All right, so today we're continuing to take a look at absolute value inequalities. And there are going to be some differences from how we solve absolute value equations, but it's still going back to that base definition for what absolute value is, and that is that it measures the distance that something is away from zero on the number line. And remember we said on Friday that distance is always measured as positive. So your answer to absolute value is always going to be a positive number. And so taking a look at this first inequality, so we have a really simple statement here. We're just doing the absolute value of x, and we're trying to find what values of x would make this true, meaning if you do the absolute value of that number, the answer you get is something that's less than 3. And so putting that into a sentence, what this actually means is that the distance that this unknown number x is away from 0 is less than 3 spaces. So here we're just going to draw a picture of what that would look like. So if the distance that something is away from 0 is less than 3 spaces, well, it could be to the left of positive 3. So all of these numbers right here that I've just shaded, those are less than 3 spaces away from 0. But another possibility is that it could be on the right side of negative 3. So look at this, everything from negative 3 all the way up to 0 on the other end, those values are also less than 3 spaces away from 0. And so what we're looking at here, this number line graph actually shows all of the solutions to this first inequality statement, meaning any number that's in this shaded region on either side, when you take the absolute value of that number, that result will be something that's less than 3. So this kind of reminds me of the regular inequalities that we were solving back in the last section, that there's an infinite number of solutions. And so we're still going to be using the number line here. We're going to be using the shading just to show where all of those solutions are. So a little different from Friday. With our absolute value equations on Friday, we were getting 2 answers. Well, this is now really representing an infinite number of answers. So we're going to do it with shading. Now, if we wanted to represent our answer, like how could we show what's on the number line graph using symbols? Well, off to the side, we could write this. Actually, I'm going to put this above my number line picture because it kind of matches with what we see on the number line. We're going to say here that x needs to be a value that's greater than negative 3, but at the same time, it needs to be less than 3. And so this is that notation that we first saw when we were talking about compound inequalities, meaning like 2 statements have to be true together at the same time. This is actually the same thing as saying x has to be a number greater than negative 3, use the word and at the same time, x has to be a number that's less than 3. So making a connection to what we saw before with that and inequality, these are some different ways that we can represent our answer using symbols. Okay, so let's take a look at one that is a little bit more complex. So we have a little bit more going on this inequality. Now, what this one is saying is that the quantity inside of the absolute value part, in this case it's 3x minus 4, we're saying that 3x minus 4 has to equal something that's less than or equal to 8 spaces away from 0 on the number line. So if we were to initially make a picture of what the original problem looks like, I'm thinking that less than 8 spaces away from 0 is going to be like out to positive 8 to the right or out to negative 8 on the left. And so what I'm going to notice here is that one possibility is that the 3x minus 4 is in this shaded region here. So in other words, 3x minus 4, it could just be less than or equal to 8. So it could be in that section. Another possibility, I'm going to change colors here to make this stand out, is that 3x minus 4 might equal something that's in that green region. In other words, greater than or equal to negative 8. And so this is going to allow us to branch off into two possibilities. We're going to be able to write two inequalities here, representing the different possibilities that we see here on our picture. So the first one that I'm going to do over here on the right was the one that I originally did in blue. So one possibility is that 3x minus 4 is just simply less than or equal to 8. So that matches this possibility. And then the one on the other side is matching here what we did in green, is that 3x minus 4 could be greater than or equal to negative 8. The greater than gets it to the right, and if it's to the right of negative 8, it's still within 8 spaces away from 0. So what I want you to notice here is that we kind of have a similar situation as to what we did with our equations on Friday, where we look at this and we have our two arrows here. We're splitting this up into these two different possibilities. Notice that here and there, we don't have the absolute value signs anymore. So this is a way to write it without the absolute value. We're going to continue moving forward, solving each inequality part separately. So I'm going to go back here to this one here in blue, so I'm just going to start by adding 4 to both sides. And then we're going to divide both sides by 3. So that's one part of our solution here, that x needs to be a number less than or equal to 4. And then on the other side here, we're essentially going to do the same set of steps. It's going to be a different result, though, because notice that the direction of our inequality symbol is facing a different way. We had a negative 8 instead of a positive 8. Negative 8 plus 4 is negative 4. It looks like this one is going to end up being a fraction value. That is fine. So negative 4 doesn't divide by 3 evenly. We're just going to keep it as the fraction negative 4/3. All right, now one way that you can express your final answer is to keep everything the way that you see it here, but just put the word "and" in between them. Because as we saw in the first problem, it has to make both of them true. So it needs to be greater than or equal to negative 4/3. At the same time, it needs to be less than or equal to 4. Now let's see what that would look like here on the number line. So less than or equal to 4 would be all of the x values over here. Negative 4/3, that's the same thing as negative 1 and 1/3. So it's approximately negative 1.333. So that's going to be a little closer to 0. I'm going to go ahead and label that here. I'm just going to keep it as a fraction, though. And greater than or equal to means that it's shading on the right. And so notice, just like we're used to seeing with the "and" problems, like that shading is going to connect, the shading is going to overlap. And so this would be a number line graph of our solution. Bless you. Now, because of the word and because we have this overlap here, now that we have our number line graph, we could actually turn it into this other version where we write it all as one statement. We could say, well, x is in between negative 4/3 and 4. So that would be a different way of saying the same thing. I think about it as like x kind of looks like it's in the middle of a sandwich. It's like literally sandwiched in between these two endpoints. So it has to be some number that's in between. So what this is representing here is that any number that we were to choose that's inside of this shaded region here, like you could choose the number 1 or 2 or 3 or even a fraction, if you were to choose that number and plug it back into this original inequality at the very beginning and solve the whole thing out, it would end up being a true statement. Now, there's one final thing that I want you to notice that I want to point out here on this problem. So going back to what we did in this very first step of splitting up the pieces, I'd like to first show you that number line picture to help us make sense of this being less than 8 spaces away from 0. So there's 2 possibilities for how that could look. But I want you to also notice something, that when we wrote out the 2 different versions, the first one, everything was exactly the same as the original problem. So notice how the inequality symbol was exactly the same direction. And notice how the sign, meaning positive or negative sign, of the number on the other side was exactly the same. We did a positive 8. So I called that one the same one. Everything's the same. But let's take a look at the other one, and let's notice something, that now the direction of the inequality symbol, it's going the other way. And so the word I use for this is opposite. So I'm just thinking in my head, it's going to be the opposite direction. I'm going to flip the symbol the opposite way. And notice that that goes with the negative 8, that was the opposite sign of what we originally had, which was positive 8. So this could be maybe a shorter way, a little bit of a shortcut to help you think about how are we going to split up the 2 pieces. One of them is same, the other one, everything's opposite. All right, let's take a look. There's another little question here off to the side in the box. We talked on Friday about how if you have an absolute value equation that is set equal to a negative number, remember this one, we said that this has no solution. Because we said the distance away from 0 cannot be negative. So that's always going to be true when we're dealing with equations. Well, let's think about what that would be if we were dealing with an inequality symbol, like a less than sign. So the situation we have here is we have the absolute value of something less than negative 5. Well, remember that this side over here, absolute value means the distance that something is away from 0. Well, the distance that something is away from 0 is always going to be a number that is positive. So I'm going to make a little note here that absolute value of x, like even though we don't know what x is, that answer is going to be a positive number. I'm just going to put the word sum in here. So that's equal to some positive number. Well, could a positive number ever be less than a negative number? No, it would never be. If you think about the number line, all the positive numbers over here, they're all to the right of all the negative numbers. And on the number line, if the number's on the right, it's bigger than the other one. And so this statement here would never be true. And so we can actually use the same thing that we did on the board when we talked about equations. This one is going to be no solution again. A positive number would never be less than a negative number. Look at another problem here, and on this one, I want you to notice that now the absolute value part, it's not completely by itself at the start. It's being surrounded by some other things. It's being multiplied by a 3 in front. It's subtracting 12 on the end. So same as what we did Friday with our absolute value equations, we do need to isolate the absolute value part first. All right, so in order to get that blue thing all by itself, we always want to deal with any addition and subtraction on the very end. We want to deal with that first, just as we would if we were solving a normal equation to get x by itself. Here we just want to get the absolute value part by itself. So let's go ahead and start by adding 12 to both sides. And something that we just want to be really careful of is that when you bring this part down, you're writing the inequality symbol. That's the same as whatever you started with. So it can be easy to accidentally turn it into an equal sign because of the equations that we've been solving, but we need to keep it as an inequality sign. All right, so we're doing that first. Now, with that 3 on the outside of the absolute value part, it's also really important to remember that that cannot distribute to the inside. It's not the same as parentheses. If this was just regular parentheses, yes, you can multiply 3 to the inside. But we're not able to do that with absolute value. Imagine that those absolute value bars is like a big, huge pole that goes from the floor to the ceiling. Like the 3 can literally not get by. Can't go over it, can't go under it. It's like a wall, like a brick wall. And so the only way to get rid of that 3 is to divide both sides by 3. And that's because the 3 was really being multiplied in the front. Well, how do we undo multiplication? We divide. All right, I'm going to actually move my next step over here off to the side. Notice how we still have the inequality sign, less than or equal to, and then 6 divided by 3 is 2. Okay, so we've now turned it into a position, a problem very similar to what we had above. I'm going to give you a few minutes here. I want you to try to finish this one out on your own. All right, so let's check and see what you have here. So, because we have gotten the absolute value part by itself, we're ready to go ahead and branch off into those 2 possibilities. So, I just always start over here on this right-hand side. And so the first one that I wrote here, so notice that we don't have the absolute value signs anymore, and everything's the same. This is the same. Same inequality symbol, direction, and it's the same exact number, it's positive 2. Now when we take a look over at this one, everything was opposite. Opposite inequality sign, and now it's a negative 2 instead of being a positive 2. Now notice how the other piece that is the same between the 2 statements on either side is that 2x minus 4. And that never changes. Never change what was in the absolute value. That's always the same. It's only the other side that we're talking about. And conceptually, if we think about what's happening on this number line, this is saying that this quantity is something that's less than or equal to 2 spaces away from 0. So if you think about 2 spaces away from 0, well, it could be less than or equal to 2 on this side, or on the other side of 0, it could be greater than or equal to negative 2. So that makes sense why these are the 2 spaces that we're splitting this into. All right, and then finishing it out, our steps are essentially the same on both. So we're adding 4 to both sides, dividing both sides by 2. And so our end result here, we end up getting that x could be something greater than or equal to 1. But at the same time, it has to be less than or equal to 3. And so to finish out this solution here, we have 2 separate parts. We need to put the word and in between them. So and is always going to be the one that's used when you are solving a less than absolute value inequality. If you start with a less than sign, we're corresponding that with and for the answer. You can also see it, though, on the number line, because when you do the numbers that are greater than or equal to 1, and then you also plot the numbers that are less than or equal to 3, you're going to see that we have some overlap. You're going to see that the shading is going to connect. And if we wanted to write the other version of our answer just using one statement where the x is sandwiched in between the other values, that would look something like this. So x literally has to be something in between 1 and 3. Or it could be equal to 1, or it could be equal to 3. The last piece that we have to look at is a greater than absolute value inequality. So there's going to be a lot of similarities here, but the difference is that the original symbol in the problem, like here or down there, is greater than instead of less than. Okay, so let's start with a simple one. So if we have something like the absolute value of x is greater than 4, what that actually means is that the value that x is has a distance away from 0 that is greater than 4 spaces away. So now if it's greater than 4 spaces away, we have a very different looking picture. One possibility is that it could be shaded to the right of positive 4, and I'm going to extend that arrow there with the shading, like that's going to go up to positive infinity, like all those numbers shaded to the right. Like that could make the statement true. It's more than 4 spaces away. Another possibility, though, let's go on the other side. So if we wanted to be more than 4 spaces away on the other side, that's going to be anything shaded to the left of negative 4. And we have like an infinite number of values there that are further away from 0 on that other side. So that's what the solution would look like on a graph. Now, if we were to write out our solution using symbols, there's 2 pieces to this. Matching the first side here, oh, I don't quite have enough space. I'm going to write the whole thing on the side, but it's kind of matching our picture. So to match this first part, I'm going to highlight that in yellow. Those are x values that are less than negative 4. Okay, so those go together. On the other side, I'm going to make that little section there in pink. And these are values that are greater than 4. Now, notice that there's no overlap here. You can't be less than negative 4 and also greater than 4 at the same time. And so because of that, it's not the word and that we're putting in between these 2 pieces. When you're doing your greater than absolute value inequalities, the word that we have to put in between is the word or. And when you do it with the word or, and you have this big gap in between the part that's shaded, there's not a simpler, shorter way to write it all as one statement. We only do that simpler way when it's the and. When you're doing or, you're just always going to write it as 2 separate parts. All right, now the other thing that we can take a quick look at here, if we connect this back to what we had in the original problem, even though this was the greater than symbol, not the less than symbol, notice that this side here of our solution, everything was the same. So look, it's the same. So that was one way of writing it. And then notice how on the other side, everything was opposite. So we have an opposite direction of our symbol. It's less than instead of greater than. So the less than sign, and then it's a negative sign in front of the 4. So the same trick works regardless of what symbol you're given at the start. Okay, so in the next piece here, we just have something that looks a little bit more complex. Notice, though, that we have a greater than sign in the original problem. This is kind of like the other one that we did where we have to isolate the part here that's in blue first. So we actually need to get rid of that minus 20 before we think about splitting this up. So let's go ahead and add 20 to both sides. Make sure that you keep your inequality symbol listed as what it is, so this is the greater than sign. And I'm going to give you another minute here on your own to go ahead and finish this one. So go ahead and try that. Think about kind of using the same strategy that we've done so far on the others. All right, so similar first step of getting this split into the two pieces. Notice though that the 5x plus 10, that's exactly the same. We're never changing that side. The one over here, this is the same version. So everything is the same as the original problem. We've got the same direction. Let's unfreeze that. We've got the same direction of the symbol, and then we've got the exact same number there, positive 35. On the other side, this is where everything is opposite. Opposite direction of the symbol, opposite version of the number. It becomes negative. So if we want the distance away from 0 to be more than 35 spaces, two ways that can happen. It can just be more than 35, or it can be something less than negative 35. So that gets us our two possibilities. Now when we solve each one separately, we end up getting that x could be something that's either less than negative 9, so that's what that left side of the picture number line on the bottom looks like, or it could be something greater than 5. So let's make sure here that you are separating your solution here with the word or. So that's going to be one part of our answer. And then I'm also going to put a big box around that number line graph. That would be the graph of our answer. So any number that's in the shaded region on either side there, if you were to take that number, plug it back in for x in the very original problem, it's going to make the statement true. All right, and then there was one last little bubble off to the side here about the greater than symbol being used. So what about something like the absolute value of x is greater than negative 5? Well, up until this point, we saw that if you have the absolute value of something equal to a negative, it's no solution. And if you have the absolute value of something less than a negative, it's also no solution. But let's think about what's happening now in this problem. So we know the absolute value always means it's going to be a positive number. So what we have here is we have a positive number on the left, and it's saying that that positive number is greater than negative 5. Well, this is actually true, right? Every positive number is greater than a negative number, right? Because every positive number is further to the right on the number line than where the negative numbers are. And so if this is true, it's not going to be no solution. This is actually all real numbers are a solution, meaning x could be anything. You could plug any number into this, and it's always going to be true because a positive number will always be bigger than a negative. So that's just kind of a little extension to think about like what would happen if you had a negative number on the other side.